Okay, so last topic, and we're still going to spend a couple of days here. We still have a couple of days to work on conservation of energy. We'll probably even get back to that today. Okay, but we want to talk briefly here about efficiency, because efficiency is something that we're obviously very concerned with. We want to make the best use of the energy that we have and not be wasteful. Okay, so if you were using a machine, okay, would you accept a machine that operated at, let's say, 10 or 12% efficiency? We like to think that we wouldn't accept that, but we do every day. That's what we have. Okay, we talked about earlier on in the unit how certain types of energy transformations are more effective than others. Okay, and what we mean by more effective is more efficient. That is how much of the input energy actually gets turned into useful work. Right? One of the least efficient energy transformations is from heat to mechanical energy. Okay, that is one of the least efficient ways to transform, or convert energy from one form to another. Anytime you convert one form of energy to another, some energy is lost. Okay, there is no 100% efficient energy conversion. That's essentially part of the second law of thermodynamics. It's why perpetual motion machines don't work. Okay, so what we want to do when we're trying to, let's say, generate a certain type of energy, like let's say electricity, is we want to have as few steps as possible from our initial form of energy to our final form of energy. The more steps there are, the more energy conversions there are, the more energy is going to be lost in the interim. Everybody with me on that? Okay. So, in this province, how do we generate the majority, at least right now, the majority of our electricity? Coal. Okay. Why do we use coal? Because there's a lot of it and it's cheap. Okay. Those are good things. Don't let Nutley tell you otherwise. Okay. Those are good things. It is cheap and it is readily available. Okay. And if it's readily available, that means we don't have to spend a lot of time and money transporting it to where it needs to be. Okay. This is the whole kind of argument against the argument against pipelines. Okay? Everyone's like, oh, pipelines are bad, right? Pipelines are terrible. If there's ever a break in the pipeline, then oil spills everywhere, and that's horrible. And I'm not saying that it's not, except that pipelines have so many sensors and valves all over the place that a massive spill from a pipeline is highly unlikely unless it was an act of eco-terrorism. Okay? If there's a small leak in a pipeline, the pipeline detects the loss of pressure and closes the valves and stops the flow of oil. And then only the oil that's between the two valves that are closed actually can leak out. Okay? What's the advantage of pipelines over the way we currently move things from place to place? Okay, some of them are underground, some are above ground, depends on where you are. Okay, what's the other advantage?
Quick transport.
Quick transport.
We usually transfer them by ship, so not a larger area.
Okay, right now, yeah, this is the problem. Right now, we transport things by cargo ship, train, and truck. What do all of those things need? They produce pollution. They all use fossil fuels to move things around. This is the flaw in the logic of the argument against pipelines, by the way, is that pipelines are bad for the environment, but allowing thousands of trucks and trains every day to burn fuel to transport the same material slower is better somehow. I don't know. Anyway, that's efficiency. Okay, which is more efficient? Okay, a large pipeline carrying huge amounts of oil and not requiring any fossil fuels, or trucks and trucks and trucks and trucks. Now, I'm not saying that there's, pipelines are the panacea of all social ills, but I mean, truckers have to have jobs too, right? Okay, so energy or efficiency is how much of your input energy actually ends up as your work being done. Now, we know nothing's 100% efficient, okay? But if we look at the typical internal combustion engine, an internal combustion engine converts heat into mechanical energy. When fuel is detonated, it gets hot. The heat causes the gases, carbon dioxide, water vapor, to expand. And when they expand, they push on the pistons within the internal combustion engine and drive them down. That's the energy that drives your car. Well, in your car, if you were to put $100 worth of gas in your car, which at current gas prices, happily, is a little more difficult unless you drive a big truck, okay? But let's say you put $100 worth of gas in your car. 33% of that $100, $33, okay, goes out the exhaust system without doing any useful work. Because it's what? Heat. And that heat didn't do anything. Okay? Most of the heat produced by burning fuel in your car doesn't actually do useful work. In fact, the internal combustion engine is so inefficient, it has to use 1/3 of all the energy in the fuel to cool itself. That is, to run the water pump and pump the antifreeze and coolant throughout the engine block to keep the engine from melting down. Okay, that's how inefficient it is. So already we've vented much of the heat because we made more heat than we needed to actually drive the piston down, and so much of that heat was there that we had to get rid of some of it through a cooling system that also took up 1/3 of all the energy in the fuel. So you've just spent 66 of your 100 hard-earned dollars and not gone anywhere yet. Okay, we haven't driven the car forward yet. Okay, this is just the energy required to keep the car from destroying itself. Okay, the drivetrain of your car, that would include things like the transmission, limited slip differentials, okay, like things like that. If you have all-wheel drive, all that kind of stuff. Okay, that all is included in drivetrain. Okay, there's a lot of friction in those parts of the vehicle, and as a result, there's energy that's lost there. Okay, as the car is trying to have those moving parts move, energy is lost. Okay, your accessories. This is for like a stock car, not the car that drives by my house and can be read on the seismograph. Okay, cars that have a really loud stereo would have a much higher number here because they may in fact have an additional power source. Okay, I knew a kid when I taught in Lloydminster who had 2 alternators on his car. Okay, the alternator is what actually like charges your battery and generates electricity. Okay, for all the accessory devices in the car. Okay, that takes about 4% of the energy in the fuel. Okay, is just to turn that little generator. That's what an alternator is. It's just a generator. Okay, but his car would drain the battery if he didn't have the second alternator on to power all of the amplifiers and subs and all that kind of stuff that he had in the car. Okay. Oh, it was, yeah. He had this, it was this like Fox body 1983 Ford Mustang. Okay. And it was all rusted out. They called it the Rustang, actually. That's what everyone called it at school. But we had a show and shine every year at the school, and the kids would bring in their cars. And he had this show that he would do called the Looney Dance. And he would flick a loony onto the roof of the car and then crank the stereo. And the loony would jump all over the roof of the car. And I'm not talking like this far. I'm talking like a foot off. Okay, it would just bounce around all over the roof of the car from the sound of the stereo. The last year I was there, in his grade 12 year, he cranked up. He had gotten another couple of subs somewhere. He had found space for them. Like, he couldn't sit in the back seat of this thing. Anyway, he started cranking it up, and the loony was dancing. And then all of a sudden, the whole rear window and the hatch shattered. Okay, because it had gotten so, the vibration had gotten so intense, and it was kind of cold out that day that the whole back window shattered. Okay, which is not a cheap replacement because it had the rear window defogger, the wires running through. So yeah, his face, it was pretty funny because he was like, oh, that was so cool. It was pretty cool, but it was probably an expensive fix. Okay, the stereo was worth 10 times what the car was worth. I never thought that it could shatter the window. No, it was, yeah, when I saw it, I was like, I should have thought of that, but it was so cool to watch it happen. Okay, other internal friction. Okay, what do you have to change on your car between every 5,000 and 10,000 kilometers? You got to change the oil. Okay, the oil is what lubricates the metal on metal parts, okay, of the car that have to move, but there's still friction. Okay, and so some of the energy is lost. So that ends up being About 14% left. Okay? So 14 of your $100 worth of fuel actually drives the car forward. Okay? Now this would be for, let's say, like a larger sedan, larger V6 engine. Okay? Is a hybrid car going to be more efficient than that? Yep, it is. Okay, it's going to be more efficient than that, provided you use the hybrid car in the right way. Okay? What kind of traffic or driving situations are hybrid cars best in? Right. They're for stop and go traffic. They're not designed to be efficient on the highway. Not that they aren't. They do have a small internal combustion engine, which isn't going to use as much fuel on the highway. Okay, but they are designed to be more efficient when you have to stop, wait for a light, and then go again, and then stop and accelerate and slow down and all of that. Okay, the reason they're more efficient there is because the electric motors in those cars kick in when the car is under load. That is when it has to do the most work, when it's accelerating. Okay, that way the internal combustion engine doesn't have to work as hard and use as much fuel. Okay, now you do have to have a bigger alternator in a hybrid car because what are you always having to do? You're always having to recharge the batteries. Okay, and oftentimes hybrid cars will even turn off the internal combustion engine when stopped at a light. Okay, and then they'll fire back up when you press the gas. The electric motors will turn on and give you that little extra boost. Okay, making a hybrid car not seem gutless. Okay, because the first kind of electric cars and first hybrid cars were really gutless. Okay, they had really incredibly small internal combustion engines and very weak electric motors. Okay, the design has obviously since then been much improved. Okay, and in fact now many of the kind of like supercars, okay, are actually hybrids. Okay? They have electric motors because electric motors can deliver a lot of power and torque immediately. Okay, if anyone like reads Motor Trend or any of those kind of magazines, a Tesla, which is a fully electric car, can actually out-accelerate a 707 horsepower supercharged Dodge Challenger Hellcat, okay, which is like the epitome of all things kind of wrong with the idea of power and fuel use, okay, but this electric car can actually go faster. Okay. All right, so certainly there are things we can do to be more efficient. A hybrid car is excellent to increase efficiency in stop and go situations where it can work. But on the highway, the electric motors almost never kick in. Okay? Maybe on a hill, like if you're going up a really steep hill or something, then the electric motors might kick in and assist the internal combustion engine. But if you're on Highway 2 driving from Edmonton to Calgary or Calgary to Edmonton, it's not going to be really an efficient use of the hybrid vehicle in that situation. All right, everybody follow there. Okay, if you get an electric car, are you being more efficient? Is driving an electric car more efficient than driving an internal combustion engine? In certain situations, yes. Okay. But here's the thing. Regardless of how I get to work, let's say I have to commute, like so many people in Okotoks commute to downtown Calgary. The amount of energy required for me to get from my house to downtown Calgary is the same, whether I take an electric car or an internal combustion engine or a hybrid vehicle. It takes a certain amount of energy to get there. Where does that energy come from? Well, if it's an internal combustion engine, it comes from fuel. It comes from fossil fuels that are burnt in order to produce power. If it's a hybrid car, it's the same thing. Okay, I'm still burning fuel, and I'm using that fuel to power myself as well as charge the batteries in the car, but it's still going to be using fuel. Okay, now you can have a plug-in hybrid that you can plug in at home, okay, and it can charge the batteries before you go. Okay, where does that energy come from though? Right, it's just still fossil fuels, right? Because in Alberta, we generate most of our electricity using coal or other fossil fuels. Is it the same then if I have a Tesla and I plug it in every night? Yeah. Okay. At least in Alberta, having an electric car is not really reducing your carbon footprint any. Okay, because we get all of our electricity through fossil fuels. So you're not really reducing your carbon footprint, okay, by doing that. So that's kind of the hole in the logic, okay? You know, like Leonardo DiCaprio doesn't want you to know that, right? That he wants you to buy an electric car because it's so much better for the environment, except in Alberta it's not. Okay? You're still getting your electricity from coal-fired generation or natural gas generation or whatever. Okay, everybody with me there? So yeah, you kind of, when you're making social decisions, if you're trying to be socially responsible, which is good, make sure that that's actually what you're doing, right? It's otherwise you just look silly, like Leonardo DiCaprio. Okay, you just end up looking silly because you say something that's not true and everyone knows it. Okay, like, you know, climate change is actually a Chinook, but not really, right? Because then you end up looking stupid. Yeah, that's why I can't listen to anything he says. Yeah, first he got that Chinook thing all wrong, and then he got on that boat, that gigantic boat that's bigger than my house. That's, I'm sure, powered by like sunshine and rainbows and unicorn farts or something. I don't know. Okay, but yeah. Okay, I'm sure it's not very efficient. Okay, so any systems with moving parts are going to lose energy as heat. Okay, they're always going to lose energy as heat. If there's moving parts, there's parts that are rubbing together. Okay, and if they're rubbing together, there's friction and there's energy lost. Okay, that's consistent with the first and second laws of thermodynamics. Okay, once you do work, work is a flow out of the system. Okay, and then the second law of thermodynamics says it's got to flow from hot to cold or from high to low. All right, so for example, all the energy supplied to your body by food must equal all of the useful work done plus all the wasted energy. Okay, does our body waste energy?
Yes.
Absolutely. Okay, our body runs at 37 degrees Celsius. That's our normal body temperature. Okay, does it need to be that hot? Well, for most of our metabolism to work, yes, but it's a lot of that energy just radiates away. Okay. All right. So according to the second law, heat always flows from hot to cold, and in the process, it can be made to do work. Okay. Is that partially why our cars don't do as well when it's cold as it is right now? Yeah, because a lot more of that heat energy just quickly runs away from the car. Okay. It bleeds out into the environment, which is comparatively very, very cold. Okay. However, during thermal energy transfer, some energy is always lost to the surroundings. Thus, the efficiency can never be 100%. Okay, that means you can never even come close to getting the energy out of a system that you have put into it. All right, so efficiency is always measured as a percentage. Okay, so what we essentially do is we just take the mechanical energy output, or the useful work, and divide it by how much energy we had to put in, the mechanical energy input. Okay, we divide those two numbers and we get a decimal that represents our percentage, just the same way you do when you're calculating what you got on a test. Okay, you take what you got, divide it by what you could have got, and that tells you how much of it you got right. Okay, well, efficiency is calculated in exactly the same way. Right? We're going to take out the multiply by 100 part because I'm sure everybody can do that part in their head. Yes? Okay. Okay. Some machines or systems involve the conversion of mechanical energy into another form of energy. Okay. For example, a crane uses mechanical energy to do work of lifting a load vertically to the top of a building, so the load gains mechanical energy. Okay. Where did the mechanical energy come from, though? Right, whatever's powering the crane, okay? The crane could be internal combustion powering a hydraulic pump, or it could be purely electrical. Right, it depends on the load required. Okay, so typically an automobile internal combustion engine, and these numbers are a little older now. Automobile internal combustion engines are a bit more efficient now. They're probably getting closer to about 20%, okay, which we accept on a daily basis. Okay, an electric engine is up to 95% efficient. Because what does it not generate a lot of? Or sound. An electric engine is a lot quieter. Okay, I found that out the hard way when I nearly got hit by a Volt. Okay, because they don't make any noise. Like, you just don't hear them coming. Okay, I was out for my morning run and I'm running along and I kind of, just quickly looked and didn't see anything. This guy turned and I never heard him coming because it was a Volt. It was an electric car. Okay, in fact, they have some electric cars where they actually have a speaker that just makes noise. Okay, that so that people can hear them. Right? But an electric car is very, very quiet. Okay, I mean, at high speed you hear the tires, on the road that makes that sound, but okay, the sound of the engine isn't there. Okay, they also don't generate as much heat. An electric motor typically doesn't get very hot. Okay, a steam reciprocal engine. Okay, 50 to 75% efficient. All right. The inefficiency comes, of course, in getting the heat to turn the water into steam. That's where most of the energy would be lost. Okay. A steam turbine engine up to 40% efficient. Okay. Do we use turbines a lot? Yeah, we do. Okay. In all of our electrical generation, okay, in Alberta, turbines are used. Okay. Whether it's coal, gas, hydroelectric, wind, it's all turbines. Okay, a turbine is essentially like a fan blade that turns really quickly because something's moving through it, either steam or wind or water. Okay, one of those things, okay, is being turned. But again, it's got moving parts. Okay, and if there's moving parts, there's going to be energy lost to sound and heat. Okay, everybody with me on that? That making some sense there? Okay. Where are some places in our house where we've tried to become more efficient? Light bulbs. Okay, light bulbs are like one of the first places where you can really save a lot of money in your house in terms of improving efficiency. Okay, usually when you get your house, if you've like bought a new one, like that's been built for you, when you move in, all the light bulbs are the old-fashioned tungsten filament incandescent bulbs. The first thing you should do is take them all out, okay, and replace them with something better. Now, when I first moved into my new house, I replaced with CFL, those compact fluorescent, the ones that look like a coil. Okay, are there problems with those? Okay, what are the problems with those? Right, they got mercury in them. Okay, so they can't be thrown in the regular garbage. You have to dispose of them properly. A lot of people didn't know that, and a lot of mercury ended up in landfills during the great CFL craze. Okay, that happened. Okay, like about 10 years ago. What's even better than CFL? LED. Yeah, okay. The newest thing is LED bulbs, light emitting diodes. They are incredibly efficient. Okay, you can replace a 60-watt incandescent light bulb with an 8-watt or less LED bulb. Okay, because how does a tungsten filament incandescent light bulb make light? Yeah, the tungsten filament gets white hot. Okay, and as a result makes a whole bunch of light, but you can't touch it after it's been on for about 5 seconds because it's too hot, right? Whereas an LED bulb, if it's been on for hours, you can just reach up and take it out. Okay, it's not hot at all, right? CFL bulb eventually gets hot, and usually you replace a 60-watt incandescent with about a 13-watt CFL bulb. Okay, so there's certainly more efficient. Okay, like I noticed a drop in my electric bill right away when I replaced the incandescent bulbs, and it was significant. Right, so there are things that we can do, okay? And when you're buying appliances, that's another thing you can look at. You can look at, there's always an energy sticker, okay? Energy Smart, I think the sticker says, okay, on there, and or EnerGuide, sorry, that's what it says, EnerGuide. And if you put it, it's always on appliances, it tells you where does this thing compare in terms of least efficient and most efficient, okay? Appliances, okay? And that can help you make your choice. You know, I know bottom line is most people buy the one that they can afford, but okay, sometimes you can look at, I can afford these 3, but this one will use the least electricity over the course of its usefulness for me. That's money that you get back then. Okay, so there's all kinds of ways within your house that you can make choices, okay, that are going to be more efficient, and in the end save you money. Okay? Like right now, I'm busy teaching my boys to turn lights off when they leave a room because they're terrible at it. Okay? I'll get ready to go to bed, turn off what I think are all the lights, and notice light coming out of all these other rooms. They've forgotten to turn the lights off. Okay? Which is why I've replaced all of the bulbs with LEDs, so that because you have little kids, you don't want to just light money on fire because they're leaving lights on. Okay, let's look at a simple example here. So I've got a crane that lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work. Okay, or mechanical energy input, right? It is only doing, however, 8.00 times 10 to the 3 joules of useful work, or mechanical energy output. So this is the energy that it used, okay? So we'll highlight that in blue, okay? It actually did 2.3 times 10 to the 4 joules of work, or it used that much energy, but only produced this much useful work, okay? 8.00 times 10 to the 3 joules. If you're reading a question and by the context of the question can't tell which one's which, how can you tell just by looking at the numbers which one's which? Yeah, the bigger one goes on the bottom, right? Okay, it's the input energy. Okay, the input energy is always going to be greater than the output because you can never be more than 100% efficient, right? If you do your calculation and you get a number greater than 1, okay, like 1 point something, then you know you reverse them because you've just broken the first law of thermodynamics and created energy from nothing. All right, so if we're doing this and we want to calculate the efficiency of this machine, okay, then we go, okay, the useful energy, okay, so EM, divided by the input energy will give us the efficiency. So that's going to be then our 8.00 times 10 to the 3 joules, or 8,000 joules, divided by 23,000 joules. Oh, nice. Sorry, I shouldn't take shortcuts. 8,000 divided by 23,000. I was just going to go 8 divided by 23. Would I got the same answer? Okay. All right, so this crane is working at 35% efficiency. Okay, 0.347 is 35% or 34.7% efficiency. Okay, everybody all right with that? Is that a very difficult calculation? All right, this formula, what if I gave you the percent efficiency and asked you to find EM? Yeah, multiply EI over here, right? It's just like V equals D over T. Okay, you could be asked to do some simple manipulation, okay, with that efficiency formula. All right, I want you guys to try those 3, okay, efficiency questions, and then I'll go through them here in a few minutes, and we'll see how we do.